Welcome to my YouTube channel. This is a question of part B of CSIR NET June 2024. Let's take a closer look at the question. Let V be the real vector space of 2 by 2 matrices with entries in R. That means V is the set of all 2 by 2 matrices over R. And we know that this is a vector space over R. Let T from V to V denote the linear transformation defined by T of B equal to AB, or all B belongs to V, where the matrix A is given. A is a diagonal matrix with diagonal entries 2 and 1. What is the characteristic polynomial of T? So the question is basically asking what the characteristic polynomial of T is. Here 4 options are given. Let's see how we can approach these kind of problems. First of all, our matrix A is diagonal matrix 2 0 0 1. So clearly 2 and 1 are eigenvalues of A. The vector 1 0 is an eigenvector of A corresponding to the eigenvalue 2, because if we multiply A by the vector 1 0 from right side, then it will be the first column of A. That means the vector 2 0, and we can write this as 2 times the vector 1 0. Similarly, the vector 0 1 is an eigenvector of A corresponding to the eigenvalue 1. Because if we multiply A by the vector 0 1 from right side, then we will get the second column of A, which is 0 1. Now I claim that if I construct a 2 by 2 matrix over R, whose one column is an eigenvector of A corresponding to the eigenvalue 2 and the other column is the 0 vector, then the matrix will be an eigenvector of T corresponding to the eigenvalue 2. So if we take x1 to be the matrix whose first column is an eigenvector of A corresponding to the eigenvalue 2, namely the vector 1 0, and the other column is the 0 vector, then T of x1 is by definition AX1. The first column of this product will be A1 0 and the second column will be A0 0, and this is 2 0 0 0, and we can write it as 2x1. So this means x1 is an eigenvector of T corresponding to the eigenvalue 2. Similarly, if I construct another matrix x2 whose first column is the 0 vector and the second column is an eigenvector of A corresponding to the eigenvalue 2, that means the vector 1 0, then we get T of x2 is AX2, and the first column of this product is A0 0 and the second column is A1 0, which is equal to 0 0, and the second column is 2 0. We can write this as 2x2. This means x2 is an eigenvector of T corresponding to the eigenvalue 2. So the matrices x1 and x2 belongs to the eigenspace of T corresponding to the eigenvalue 2. And it is obvious that the vectors x1 and x2 in V are linearly independent. Clearly, x1 and x2 are linearly independent vectors in V. From this, we can conclude that dimension of the eigenspace of T corresponding to the eigenvalue 2 is at least 2. Similarly, if we construct a 2 by 2 matrix over R whose one column is an eigenvector of A corresponding to the eigenvalue 1 and the other column is 0 vector, then the matrix will be an eigenvector of T corresponding to the eigenvalue 1. That means if Y1 is the matrix whose first column is an eigenvector of A corresponding to the eigenvalue 1, that means the vector 0, 1, and the second column is the 0 vector, and Y2 be the matrix whose first column is the 0 vector and the second column is an eigenvector of A corresponding to the eigenvalue 1, that means the vector 0, 1, then Y1 and Y2 are eigenvectors of T corresponding to the eigenvalue 1. So the matrices Y1 and Y2 belongs to the eigenspace of T corresponding to the eigenvalue 1. Clearly the vectors Y1 and Y2 are linearly independent in the vector space V. Y1 and Y2 are linearly independent in V. Therefore, the dimension of eigenspace of T corresponding to the eigenvalue 1, that is dimension of E1, is at least 2. Since V is a vector space over R of all 2 by 2 matrices with entries in R, dimension of V over R is 4. Therefore, degree of characteristic polynomial of T is 4. Since 2 and 1 are eigenvalues of T, x minus 2 and x minus 1 will be factors of characteristic polynomial of T. So let the characteristic polynomial of T is Ctx equal to x minus 1 to the power n1 into x minus 2 to the power n2 into some non-zero polynomial fx, where n1 is the algebraic multiplicity of the eigenvalue 1 and n2 is the algebraic multiplicity of the eigenvalue 2, and fx is a non-zero polynomial in Rx. Let us now compare the degrees of the polynomials of both sides. So degree of Ctx equal to degree of x minus 1 to the power n1, x minus 2 to the power n2 into fx, which implies degree of Ctx is 4 and degree of the polynomial x minus 1 to the power n1 into x minus 2 to the power n2 into fx is n1 plus n2 plus degree of fx. We know that the algebraic multiplicity of an eigenvalue is greater or equal to the geometric multiplicity of that eigenvalue. n1 is the algebraic multiplicity of the eigenvalue 1. Therefore, n1 must be greater or equal to geometric multiplicity of 1. And the geometric multiplicity of 1 is the dimension of eigenspace of 1. And we have already seen that dimension of eigenspace of 1 is greater or equal to 2. So, this must be greater or equal to 2. And similarly, n2 is greater or equal to geometric multiplicity of 2, which is the dimension of the eigenspace of 2. And we have seen that dimension of eigenspace of 2 is greater or equal to 2. So, this is also greater or equal to 2. If degree of f of x is greater than 0, Then from the relation star, we get 4 is greater than n1 plus n2. n1 is greater equal to 2 and n2 is also greater equal to 2. Therefore, this is greater equal to 2 plus 2, that is equal to 4. That means 4 is strictly greater than 4, a contradiction. So, degree of f of x must be equal to 0. That means f of x is a constant polynomial. Say f of x equal to a0. Now, as the characteristic polynomial of t is monic, we must have a0 equal to 1. Therefore, 4 equal to n1 plus n2, from which we have n1 equal to 4 minus n2, and this is less equal to 2 since n2 is greater equal to 2. Similarly, n2 equal to 4 minus n1, which is also less equal to 2 because n1 is greater equal to 2. Thus, n1 is equal to 2 and n2 is also equal to 2. Hence, the characteristic polynomial of t is x minus 1 square into x minus 2 square. So option 1 is false, option 2 is false, option 3 is true, and option 4 is false.